Okay, so let's start. So welcome everybody to the webinar of today. The speaker of today is Sébastien Galtier, and he will talk about wave turbulence in the solar wind. So as usual, introduce the speaker very briefly, and then I will leave him the floor. So Sébastien Galtier obtained his PhD at the Observatoire de Nice in 1998 under the supervision of Professor Nick Poquet. His PhD was on MHD turbulence and intermittency. He joined the Mathematics Institute of University at Warwick in 1999 as a postdoc, before to obtain a permanent position at the University of Paris-Sud in 2001. He is now professor of astrophysics at Université Paris-Saclay in the Laboratoire de Physique des Plasmas. He was awarded as junior and senior member of the Institut Universitaire de France, IUF, and his research interest is on turbulence in astrophysics and cosmology. He used both high-level mathematics tools and massive numerical simulations to study the properties of turbulence and discover new fundamental laws. The domains of application are diverse: solar wind plasma, supersonic interstellar medium, solar coronal heating, dynamo in stars and planets, and primordial gravitational waves. Magnetohydrodynamics and general relativity are the main equations used to investigate these questions. So it's with great pleasure that we have here today Sébastien Galtier for the seminar of the LMFL. So Sébastien, I stop sharing my screen, and you can start sharing yours.
Is it okay? Can you see my screen?
Yes, perfect. Okay. Perfect.
Okay, let me just. And this is allowed. Okay. Well, so thank you very much for the invitation. And let me just do one last thing. I would like to remove. Okay, let me. Sorry. Well, okay, good. So and thank you for this introduction. So this seminar is about wave turbulence in the solar wind, and I will try to explain the main questions and what we have done recently, actually with papers published this year. Okay, how can I go to the next slide? Okay, here. So this is to explain the solar wind. This is just a simple, nice picture. You have the sun on the left and the Earth on the right. And the solar wind is just a wind produced by the sun. And then you can see this medium like a wind tunnel where you have a natural source, the sun, and where we can have very precise measurements. As you can see at the bottom, you have a spacecraft called PSP, Parker Solar Probe, which is the latest one. And I mean, the beginning, oh, sorry, you cannot see maybe what it is written at the top, or at least I cannot see that.
We can.
Okay.
We don't see the banner.
Okay, so this is Parker, the name of Parker, because he proposed in the 60s that wind should exist between the sun and the Earth, and it was discovered later with the first, I would say, spacecraft observation. And well, so since this time we know that the wind exists and it is turbulent, and sorry. And like PSP, this is the latest one, PSP actually Parker Solar Probe because of Parker. And what you see at the bottom, it's fluctuations of the velocity field. You have the unit, kilometers per second in time. And here for 2 hours, you can see the fluctuations of the velocity, and below the fluctuation of the magnetic field. The measure is made in nanotesla. So we have very precise measurement of the magnetic field. And clearly you can, I mean, accept the idea that it is turbulent. You have a lot of fluctuations. So it is turbulent, and but we also have waves. And the first detection was made by Galtier and Davis in the 70s. They observed alpha waves. Alpha waves are MHD waves, incompressible MHD waves. And so this is very well known. We do observe these waves. And we also know, as I have tried to show in this picture, the waves going outside of the sun are more important than the waves going back. It's mainly, sometimes it's in equilibrium, it's balanced, but it's mainly imbalance. So it's natural to talk about wave turbulence, because waves and turbulence is easily observed. At the bottom, you see again, so this number, I mean 0.15 AU. 1 AU is the distance between the sun and the Earth. And 0.15 is really close to the sun, and it is really a big improvement compared with what people have done before. And they found new results, and I will show you these results in this seminar. Okay, so waves are easy to observe, and there are actually many waves in plasma physics. That's why it is very interesting if you like wave turbulence, because you can play with wave turbulence and easily. At MHD scale, that means at the largest scale or the lower frequency, we have alpha waves and the two compressible waves called fast and slow magnetoacoustic waves. So this is a domain of MHD, and this is not the domain that I will talk about today. This is at lower scales, smaller scales. And at smaller scales or higher frequency, we have two new waves called Whistler waves and kinetic alpha waves. They are very similar. One is mostly incompressible, and the other one is slightly compressible. And we can even consider other waves if we go at higher frequency. But we do observe waves, and we are able to actually resolve MHD scales on what I call sub-MHD scale or electron scale. That means the red part here. So that means we have waves, and we can even, for a given scale or a given frequency, have different waves. So this is actually very rich, and even because of that, difficult sometimes to do wave turbulence, because we have to deal with the different kind of waves. So this is an observation made inside the sun, close to the Earth. That means at 1 astronomical unit. And what you see, it's the spectrum. I suppose you know what is a spectrum and turbulence. There is a team on turbulence, so I do not need to introduce that. This is so the spectrum for the magnetic field. You see the unit nanotesla squared, and here it is a measure in Hertz, because when a spacecraft is somewhere, you get a time variation. But it's like because the wind is very fast, you can just make, I mean, it is a proxy to actually measure the space variation. So you can just think that it is not a frequency spectrum, but a wave number spectrum. And actually, as you see, you have different power laws, and you see many decades, 8 decades. And I think it is not possible in physics to observe or to measure experimentally a spectrum, bigger than this one. So we have 8 decades. And you see that the physics is very rich, because we have the AMHD scale, where it is like Kolmogorov, -5 But then, and this is a domain where I will actually talk here, where I will be, it's steeper. You have a transition, and then a spectrum which is very close, and very often close to -8. And this is a domain called electron turbulence, because we follow the dynamics of electrons. And actually here you have two values, rho I and rho E, which are actually, as you see at the top, there is this motion. If you have particles like an electron, and if you have a magnetic field, you know that the motion is like this, and the radius is called the Larmor radius. So for electrons, it's like 2 kilometers, and for ions, actually protons, it's like 100 kilometers. And you really see that the transition comes just after that. Here at the bottom left, you see a kind of, instrument. It's called search call, and this is with this kind of instrument, built in my lab. There are big specialists on this kind of instruments. This is with this that we are able to measure the second part of the spectrum in this line, because you have two data here, two data source of data. I mean, this is another, this is called ACE, and at higher frequency, it's cluster. Okay, so this is an observation, and in terms of interpretation, like turbulence, we know that the source is the sun, of course. And if we use a classical, we'll say interpretation, we have a cascade. Of course, the cascade is for the total energy, but if I just apply here this idea on that spectrum, you have a flux, a cascade, and one big question is what happens when we go from MHD scale to sub-MHD scale? And this arrow in red means actually that we may have some dissipation here. But clearly you see different power laws. So it's not like Navier-Stokes. So you have to just to think that we cannot just say that it is a viscosity because the medium is diluted. When I say diluted in a small volume, like you take 1 centimeter by 1 centimeter by 1 centimeter, you have like 10 particles. So it's not a lot. So it's diluted plasma. And so viscosity doesn't mean anything. And we need, I mean, to consider another physics. And actually, as I will explain, we may think that there's some dissipation here, but not in this domain. Okay, where there is a 8. So this is where we have also waves. We do observe kinetic Alfvén waves and Whistler waves. So, and Alfvén waves for the MHD domain. So MHD, you know Navier-Stokes very well. MHD, it's just the same plus magnetic field. So the first equation is similar. The second one is different. This is the Newton for you. So the Lorentz force or Laplace force. And but for in plasma physics, this new tilde is not really relevant. And finally, the new thing happens here below the third equation because we need to consider the Maxwell's equation and to consider what we call the induction equation. So it's the evolution of the magnetic field. So usually the standard MHD is corresponds to the first term. But if you add the first correction called the Hall effect, you need to include this new term. And this is actually very important because this is where you can actually explain kinetic Alfvén waves and Whistler waves. And we have this resistivity, and but for turbulence, they are not so important for the analysis. On the right, this is my book on MHD, published in 2016, where you see on the front cover a simulation of actually weak wave turbulence in MHD. And in this case, the mean magnetic field that you need for your wave turbulence is transverse to your screen. It's a very strong magnetic field. Then you see this physics, this picture. We have this picture. So for my presentation, to simplify, I will just take Whistler waves. So I'm going to consider the incompressible limit. But the physics and the results are absolutely the same for kinetic Alfvén waves, which are weakly compressible. I mean, the waves, the dispersion relation is the same, and the weak turbulence equation are the same. So just it's better to do that. So if I assume incompressibility now, the equation I would say is that you know the equation for U is the same, except that first of all the pressure is different. As you see on the left, sorry, you have the magnetic pressure, where B actually is written. Where is it? B, it's not written. Little b, it's just, it's here. Here, little b is magnetic field divided by this normalized quantity. So little b is like a velocity. Okay, the unit is a velocity. So you can just imagine that it's a magnetic fluid. So you have this new term here, and below you have the induction equation, which is simplified, and especially you have a new length scale, di, which tells you something about the relevance of the whole term. You need to be at a scale smaller than this scale, di. So in my talk, I will be at a scale smaller than di, and di for the solar wind is about 100 kilometers at the level of the Earth. Okay. So basically, I'm going to consider correlations shorter than 100 kilometers. Okay. So if you solve this system linearly, you get waves, of course. So let me explain this result here on, first of all, for alpha waves. Maybe if you know one wave is alpha waves. So alpha waves, it's the following. If you have a perturbation, if you have this situation initially, you have a perturbation, then you can observe propagation of alpha waves with the speed called the alpha speed, actually, which is actually here in my unit is a velocity. The dispersion relation is given by that, and actually, if you solve the whole system, I mean, for incompressible whole MHD, you get actually not one wave but two waves, so the solid lines, and of course at small scale, so when k goes to 0, you get the alpha waves. But the novelty is that at higher frequency you have this solution which is very complicated, but this is interesting to follow. First of all, this branch here, which goes to high frequency. And you can understand, I think, that if we are at high frequency, that means the time scale of your problem is very short, and we basically follow electrons. Don't forget that in my model, we have electrons and protons, but clearly at high frequency, we follow electrons. Actually, this is the reason why we called also the model in this limit electron MHD. In this limit, you see that the dispersion relation is much less complex than for the full case, and you have the relation. So it's dispersive. Okay, k parallel times k. Parallel means along the midfield. And you have below another wave, which looks like actually inertial waves. If you know rotating Navier-Stokes, you get the same kind of dispersion relation. In plasma physics, you see that it is localized here. And actually, this is dynamics given by protons, ions. I mean, when I say ion, it's proton. Okay. So this is what you get here. In terms of polarization, we say that it is right and left. This is what you get from the dispersion relation. Okay, so this is my introduction about waves. We have many waves, and in my case, I will be here. So at a given k, so basically I have two waves, but I will consider high frequency, so that means mainly this one. Okay, so this is what you see here. This is my limit. If you take this limit, so now I come back to the system, then that means you need only to solve actually the equation for little b here, where this term will be the dominant one. That means if you can neglect these two terms, basically you have an equation for b and you can forget u. Actually, in MHD, if you know a little bit MHD, u, it's a kind of mean velocity. So it means that you follow mainly ions. So in my case, because I am a high frequency, we can say that protons, they move very slowly. So u is equal to 0, it's equivalent. Okay, so this is the system that I want to solve, and I'm going to show you data and also simulations and the theory. But what you have to know in this system, we have two invariants, energy and helicity. By energy, I mean magnetic energy, and by helicity, I mean magnetic helicity. So basically, we have two opposite cascade in this system, in principle. Okay, so now let me explain the physics, what we understand today. You have two papers at the top, 21, 22, and here this is a picture. This is the sun, okay? This is a field line, and as I said, we mainly observe waves going outside of the sun. So it is not balanced, it's imbalanced. The point is that if it is imbalanced, from the point of view of electron MHD, it means that we have a magnetic helicity. If it is balanced, the magnetic helicity is 0. So if it is imbalanced, we expect an inverse cascade. Okay. So let me explain on this picture again. I come back to omega versus k, which is normalized. So imagine that you have a cascade. We go from MHD. Okay, we follow this line, and then we arrive to small scales, all in the green line, in green domain here. But when we arrive into the green domain, because we mainly are in a situation of imbalance, turbulence, then we have magnetic helicity, so we have an inverse cascade. So we have the rate here part. So we have a kind of conflict between the direct cascade and the inverse cascade. And the way to solve the problem that was proposed by Meran and Squire is that to say we have a channel, fortunately, to push this energy into ion cyclotron waves. Okay. So then when we arrive to the green part here, we expect to have actually a balanced turbulence. Okay. But between MHD and electron MHD, because of the channel, we have actually a drop in the magnetic fluctuations. And if you see now, if you look at the spectrum again on the left, you see that in this yellow part, we have indeed a decrease, a significant decrease of the magnetic fluctuations to arrive in the domain where electron MHD is valid. So that means, I mean, we understand that as, I mean, with this mechanism. So basically, this is the reason why we believe that if we start with strong wave turbulence, because this is what we observe at LMFL scale, we should get, if it is imbalanced, weak wave turbulence at electron MHD scale. So let's see what happens in the data, and then the theory and the simulation. So this is the data, the latest paper published in Nature and Astronomy by Barwan et al. I am not involved in this paper, so I just say that this is what they observed. First of all, on the top left, you see the energy spectrum in K, so normalized with DI. We know that if you are on the right, it is this electron MHD. And there are two colors. So basically, yellow means that we have data where turbulence is balanced, okay? And actually, you see that there is no drop in the fluctuations. We change slightly the power, but there is no drop like for the black or the dark curve where there is an imbalanced situation. So this is really a way to confirm that the model proposed by this guy is indeed nice. And especially if you look at it on the right, you have the polarization, which tells you something about the type of waves. When it is dark, that means we have, if you remember the plot, we should have cyclotron waves, ion waves, proton waves. And indeed, we have a significant higher of waves when it is dark. And when it is yellow, it's really small. So that means the way to push some energy into this channel is much lower. And it is indeed confirmed by the fact that there is no drop here in this spectrum. Finally, below, this is interesting for turbulence. If you look at now the PDF, so for delta B, the increment of P is magnetic field, you see that we have the classical behavior for the yellow part with a non-Gaussian tail. But when we go to the dark part, it's close to Gaussian, not exactly, but close to Gaussianity. And now if you look at this zeta P versus P, I suppose you know what it is in turbulence, you see that indeed for the dark part, it's monofractal meaning. So we really have a different behavior. And we do believe from, I mean, I will show you that today we understand this monofractal behavior as a signature of wave turbulence. By wave turbulence, I mean weak wave turbulence, okay? And for the yellow part, it's classical. So this is published in 2024. Actually, this is known for many years. The first paper was published in 2009, actually. And you see here at the top, I mean, the main plot, this is what we observed at high frequency in the domain of electron MHD. And the little plot here, it's in the MHD domain. MHD is like, I mean, Navier-Stokes, it is intermittent, it's classical. But this observation was not understood, and actually during 10 years, people just forget this data. And 10 years after, they started to come back, like in 2021, and they found that, well, indeed, it is observed with another kind of spacecraft, and as you have seen in the previous plot slide, it is indeed well observed. Okay, so now let's go to the theory and try to understand the physics, and I will try to convince you that I would say strong wave turbulence cannot explain the data when it is monofractal. So I come back to the model here. This model was analyzed many years ago by Biscamp et al. And there is this paper where they made this for the first time a simulation, and where they predict by very simple, with a very simple and classical Kolmogorov phenomenology, a spectrum in K-7/3. So it's very classical, just you have to take into account that in this problem, if you compare with Navier-Stokes, you see you have two nablas. So you need to incorporate this second nabla in your analysis. So basically that means here L squared instead of L. And then if you do your phenomenology, you get, of course, not 5 sub, but 7 sub. This is where we were observed in simulation here in 2D, but even in 3D today. And later in this paper, they observe that in strong wave turbulence, basically, it is intermittent. So I would say no big news. This is what we know. I mean, in many cases, especially in isotopes. But this is not compatible with the solar wind. Clearly today, everybody is. I mean, except when it is balanced. Sometimes it is balanced, okay. But when it is imbalanced, which is a dominant situation, it is not compatible. So we need to go to wave turbulence. So wave turbulence means analytical treatment, means big equations. I will not show you the details of the derivation. But basically what you know, I'm sure, is that it's like rotating turbulence, actually. Because the wave in this problem are helical. So you need to use this complex helicity basis that you see here, which I use many times. I just cite here 2 papers, Cracknine and Walef. And when you decompose your problem, everything becomes very simple, or almost, and you arrive to a wave equation. So let me say what it is. Little a is the wave, if you want, the Whistler wave, because it is incompressible. So the wave here, and you see the nonlinear interaction on the right, which is a quadratic, because actually the nonlinearities are quadratic. And here I have also decomposed the fluctuations with an amplitude and a phase. Okay, so as usual, if we do that, we get on the right here this complex exponential where you mixed different, basically three frequencies where we have to satisfy, of course, k is equal to p plus q, and omega is written there to remind you this is basically dimensionally k squared, but it's k parallel k. Okay, so this is what you have to do, and the first step in wave turbulence, before going in this analysis, it's to study the resonance condition. The resonance condition is very important because you basically claim that to get a non-negligible contribution, you need to cancel G, KPQ, and of course, you need to satisfy K is equal to P plus Q, right? If you do that, you will, it's next slide, sorry, you will get what we call the resonance condition. Here, this is just a step that you need to do. You have, it's very technical. It's a local decomposition, but basically this is a classical equation, almost the same as before, except that now locally you can write with a simple manipulation your big operator M like that. Okay. So the comment here is that S. Okay, I should say what is S. S is if you take a given vector, wave vector k, you have 2 possibilities for the wave. The one can go along k in the same direction, so then S is plus 1. And if you have a wave going back, it's minus. Okay, so S just tell you it's plus or minus the direction of the propagation of the wave, and then you have a combination like that. Okay, so you can see here that it's better to have SQ different from SP, because if you think that Q and P are almost, similar in amplitude, well, the contribution is much greater when SQ is different from SP. So basically, this is what I'm going to use here to explain this cascade. So you have to solve this, like for rotating turbulence, actually. You have to solve this kind of relation. And for the first relation for the wave vector, if you take the parallel component, which is along the magnetic field, then you play a little bit with the 2 equations, you arrive to this second relation, which is exact. There is no approximation. This is exactly the same as the system before. I just took here the parallel contribution of the wave vector. And there are a lot of physics, actually. You can conclude that the turbulence, like rotating turbulence, actually, is mostly anisotropic. So let me explain the idea. Imagine that you start your simulation or your experiment with an excitation where K, P, and Q are of the same magnitude. So basically, now if I do just a simple analysis, it's not exact. If I say P and Q are about the same, so I can basically simplify and remove P, K, and Q. So then I arrive to a relation between SP and S, SQ and SP, and so on. And now, if I say that S, let's take the middle one, SQ is not equal to SP, that means here at the numerator, I have like +2 or -2. And let's assume that K parallel is fixed, some value, like, I don't know, 1, 2, 3, not 0. Then you have a finite value. Now, if I go here, let's say on the right, and if I say now that S and SQ are the same, because actually you have 3 possibilities, so you must consider one of these, then S minus SQ must be equal to 0, right? So then you get 0, because of it is an approximation, it's approximately 0, but that means below you must also take 0. So if P parallel is 0, then in this case, that means physically the cascade along the parallel direction will be very small, actually. It's not exact, but this is an indication that the problem here is like rotating turbulence is mostly anisotropic, okay? Cascade will be transverse to the mean field. Okay, that is important because for the future, basically we know that from the simulations, from observations, but for the analytical development, we can take this limit for the spectrum, as you will see later. Okay, so now, after this simple analysis, we can try to predict the power of spectrum. So again, this is a phenomenological analysis, and I will show you the analytical part just after. But we can do that easily. It's more complex than for Kolmogorov, but we can easily do that in a few lines. So basically, we have 2 time scales, the nonlinear time, which is taken from the nonlinear term. You should get K here, but because of what I have said before, because the cascade is expected to be anisotropic, you can just say that it is K perp. Then we have the wave time, which is basically K parallel, so K perp, namely K parallel in the denominator. And in wave turbulence, we expect that the wave time is very small, very short compared to the nonlinear time. And then if you define the cascade or the transfer time in this problem for 3 waves, the model that you have to use is this one, TML squared divided by the wave time. So basically, it's the wave time divided by a small parameter, which is the wave amplitude to the power 2, okay? So then you develop your phenomenology. It is anisotropic. So at the end, you get this prediction, which is different for perp on parallel K, okay? And as I say, because the cascade is mainly transverse, -5 half is the best, the most important prediction. Okay, so this is what you can predict, and this is actually also the solution that you will see later. So wave turbulence, what is wave turbulence? I need to explain a bit what is wave turbulence, because we need waves, like here on the sea, it is maybe you recognize if you are expert, this is near Carges, but you have to be very expert. And this is waves, and well, basically there are assumptions. So we need a weakly nonlinear system, okay? So you assume that waves have a weak amplitude. That's why you have at epsilon, okay? This problem is a multiple time scale problem because the first time in your system is a wave time. So you see basically oscillations. This was actually mainly developed by Bede and Safman in the 60s. And they also found that actually, because of that, the closure problem is solved in this case. And there is a natural asymptotic closure. That means if you take the long time limit, you have a lot of basically mathematically integrals, oscillating integrals, and you get a closure. And what did especially Zakharov, you can find solutions, exact solution to your what we call kinetic equation, the equation for this system. So this is what I'm going to show you here. Just before that, there are 3 books. The famous one by Zakharov, Volvo-Ifakovich, published in 92, I guess. And of course, Sergei Nazarenko, it was, I think, 2011. And more recently, here, last year, actually, I published this book on wave turbulence. And again, I like very much the front cover because it's a simulation. And in this case, it's a simulation of gravitational wave turbulence, so cosmology. I show you first of all the waves on the sea, because actually this is the first domain where the analysis was done by the Russian community, especially Zakharov, with capillary waves and gravity waves. Okay, but gravity waves is not gravitational waves. Okay, this is different. Okay, just to give you a picture in astrophysics, a good example, I think it's coronal loops. This is not my topic, but because the picture, the images here are very nice. This is magnetic loops, coronal loops, and this is the surface of the sun. And basically, the idea is to say that waves, alpha waves, imaging waves, are produced at the bottom here and as a footprint, and then waves propagate, there are interactions, and you can produce alpha waves. But this is not really what I want to tell you here. It's topic is the solar wind. Okay, so then after this big calculation, you get a big equation called the kinetic equation here for the magnetic energy and for the magnetic helicity. In my situation, actually, as you have seen, when you reach weak turbulence, because part of the energy is put in the channel of proton wave, ion waves, that means it becomes balanced. Balance means H is equal to 0, so I can just forget H for my analysis. This is an old paper, actually. So you get this equation, epsilon square means there is a slow variation. This is valid only for the resonance manifold when the resonance condition is satisfied. And below, I show you the same equation for rotating turbulence. And it looks similar. If you look at the first line, you see these are many similarities. And as you will see later, it is even stronger in a very specific limit. While the waves have a different wave frequency, but they are helical, and actually the physics, I think, is very close. Okay, so the solutions that you can get here for this problem, I will not show you the technique, but this is basically what I have shown with the phenomenology. It's a spectrum which is in K per minus 2.5 for the perpendicular direction. This is the most important contribution. Okay. So you have the theory, we have predictions, and what we know we want to do is to compare with data. And now we need to go to the simulations, the DNS. Okay, so this is more recent paper. So the code is called Asterix. You can imagine it's written by a French guy. The resolution is given here for that simulation. A high resolution transfer to the mean field, low resolution along the mean field, because we know that the cascade is weak, so we don't need to resolve strongly this direction. 0 is 1, that means the fluctuations are small, very small. And actually, there are two simulations that I'm going to show you. The blue one is for weak turbulence. So the injection is, I would say, weaker. The flux is weaker than for the red one, which is strong wave turbulence. Okay. So in both situations, you have waves. Actually, in this case, it's kinetic alpha waves, but as I said, the physics is the same as for Whistler waves. So just this is exactly the same problem. So two simulations. The mean field is along the Z direction, and you can start to see a difference. On the left, this is the magnetic field fluctuation. You see less structures than on the right for strong wave turbulence. This is what we have in mind. I mean, this is the fact that because of the phase mixing, structures are less important in weak wave turbulence than in strong wave turbulence. When I say wave turbulence, this is implicitly weak wave. So now let's go to the details of the simulation. So on the top left, you see the simulation. So blue means weak, red means strong wave turbulence, and chi is a ratio between the wave time and the nonlinear time. I remind you that for weak wave turbulence, this ratio must be small. At the top, you see that small compared to 1, because it's a ratio between the two times. And you see that for any kz, because you have many plots, because we plot here for different kz, everything is below and significantly below than 1. Okay, so this is really a situation where we expect to measure weak wave turbulence. For the other stimulation, it's different. Sometimes we can be much lower, but also when it is much lower, that means kz large, and actually that means energy small. So the most important contribution is the dark one, which is actually on the value is 1 actually for most of the of the K perp. So that means it is compatible with strong wave turbulence. Again, this is a picture to show you where we are. We have many planes between, and waves propagate from one plane to the other one, and information goes to one plane to the other one. The second interesting quantity to see to check that your simulation corresponds to wave turbulence, it's when you plot omega versus K, normalized, K perp here. And especially for wave turbulence, we expect to recover the wave dispersion relation, okay? That means in your box, information is, even if it is not trivial when you see the data, it's actually it corresponds to many waves. And this is what you observed actually. If I do not go into much detail, different KZ means different omega, and this fit means that it is indeed in coherence with this idea. However, for strong wave turbulence, you feel a large domain that includes the domain that you have at the top. So that is, an indication that it is not weak wave turbulence. Okay, we also have done that for other problems like MHD, and this is not only MHD. This is known in wave turbulence community. Then we arrive to the classical quantities, spectra. You see here blue on red and comparison with the expected solution. At the top, it's an analytical solution, -5/2. At the bottom, it's a phenomenological prediction, -7/3. It is compensated here in the little plot to show that one is better than the other one, even if the difference is not so big. But this is just for the spectrum, so we can go actually to higher. Sorry, here. Okay, we can go to the higher level for the statistics. And first of all, if we plot, this is the PDF of the fluctuations. You see a big difference with in the strong wave turbulence. It is mostly non-Gaussian, clearly. However, for weak wave, it is close to Gaussian. And at the end, when we plot zeta p versus p for the magnetic field, we see a big difference. And the blue is monofractal, whereas the red, it is not. And actually, the blue corresponds to, it is close to the data in the solar wind. And we have even a model for the strong wave turbulence, but I will not go into these details. My claim here is to show that weak wave turbulence is relevant for the solar wind. Okay, so that's nice. And actually, this behavior observed in this system numerically was also found for gate rotating turbulence. I like to make this comparison because you see here in this new slide on the left, you see an experiment where you see plots where it is actually monofractal for fast rotation. This is an old paper. It was also observed by Mini et al. In a simulation. So when rotation is fast, it is mostly monofractal. This is an observation that you have already seen. There is a further difference because for both problems, the prediction is actually K perp -5/2 for the perpendicular cascade. However, as I said in the data, for rotating turbulence, -2.5 can be observed. We can be convinced more or less with, for example, the last paper by Monsalve by the group in FAST in Saclay, or also simulations. And but for the solar wind, it's 8, so it's a little bit different. So we need to understand, and this is the last point of my presentation, to understand why there is a slight difference. And the main argument that I would like to sell is that in the first case, Navier-Stokes, it's a viscous medium, but for plasma physics, it's not. It's a collisionless medium, and it makes a big difference, I think. This is my point of view. So how it can make a difference? This is my last comment. So to get this, I would like to simplify the problem. So you have seen this big kinetic equation, right? It's difficult to simulate or to understand. But what you can do is to make an assumption and to say, I'm going to study the superlocal interaction. So that means, especially for the perpendicular wave numbers where you have the cascade, that means you say that K perp, P perp, and Q perp are almost the same. There is a small difference. And basically, that means you expand you tailor expand your kinetic, your big equation. And then you arrive to this very simple system. You see here, this is a diffusion, nonlinear diffusion equation, which is very simple. I mean, this kind of equation is known for Navier-Stokes. It was modeled. Here it's slightly different because we derive analytically the kinetic equation of with turbulence, and then we tailor expand. So there are some, I would say, I mean, rigorous derivation behind that. And the point is that actually, if you do the same calculation for rotating turbulence, you get the same equation, except that the coefficient C is different. But formally, it's the same, absolutely the same equation. So that's why it is interesting, because the similarity is absolutely strong in this case. Okay, so quickly, we have, of course, two solutions. The solutions, I mean, the stationary solution, what we call the Kolmogorov-Zakharov spectrum in -2.5. It is a solution of the problem. Fine. And there is also this, what we call a thermodynamic solution. That means if you take a power law K for E, then you have K over K, that means a constant, the derivative is 0, so there is no flux, nothing. It's not very interesting for turbulence, but it is also a solution, which is also a solution for the kinetic equation. Okay, so what I want to tell you now is that, well, why it is interesting. It is interesting because you can do a simulation of this, very precise simulation. And we arrived to this interesting property that is known for now a couple of, I mean, say, 15 years, that in this kind of equation, we very often observe what we call an anomalous spectrum. So let me explain what is an anomalous spectrum. That means a spectrum which is not the solution, the stationary solution. So basically, this is a simulation of the diffusion equation where you have a new term here just to be sure that you call it stable. I do not pretend that there is any significant physical significance here. And then you start your simulation, as you see here. So this is blue, okay? And then you have a propagation of the spectrum, and we have an acceleration. And basically, before reaching the diffusion, I mean, the resistivity here, the diffusion part, the spectrum observed is close to -8 sub. I do not claim that it is a solution, but if you fit with that, it fits very well. It's not therefore -2.5. And again, I mean, I show you a plot of the where we observe the solar wind -2.67. So that is, I mean, fully compatible with that. The flux is not constant. This is the main thing, is that during this propagation, the flux is not constant. That's why it is not the solution that you expect. Why it is interesting? It is interesting. I think I don't have a lot of time now, so I will quickly go to the final comment. It is interesting because, first of all, if you try to understand this solution, you can prove that this is a self-similar solution of the second kind. Again, it is known in wave turbulence, not only in wave turbulence. If you put this kind of expression in your diffusion equation, you can prove that that indeed everything is compatible. The measure is compatible with this expression. This is just to show you that. Well, I will not go into much detail, but you get a finite. If I come back, sorry. If you are okay here, actually we can. With this analysis, we can show that we have an acceleration of the spectrum, and we have a finite time. In finite time, we should reach K equal to infinity. Of course, it's finite, but this is what we have observed with the blue curves. That means that T star, this is Kf, this is the front. It goes very fast to infinity. Okay. Well, so why it is interesting? Because if you continue the simulation, then you reach the boundary, the diffusion, and then your spectrum changes completely, and you get finally what you expect, 2.5, and the flux is then constant. This is a stationary solution. However, and this is the main conclusion of my presentation here, is that this is a situation where we assume some viscosity at small scale, but there is no viscosity in solar wind. Actually, it's possible for the spectrum to propagate at higher wave numbers, higher frequency, and there is no mechanism like that. There are some dissipation, but it is more complex. So if we believe that situation is different, then we should consider -8 sub as the solution of the problem. And it turns out that this is what we observe. So this is, I would say, a nice conclusion for my presentation. This is a summary. The first main information that is that wave turbulence is naturally observed here in the solar wind. It's anisotropic, and we have this particularity that this turbulence, wave turbulence, is monofractal. I have introduced the word collisionless wave turbulence just to say that we should consider actually the non-stationary solution as a relevant solution for the solar wind, because there is no collision, no dissipation of viscosity, or there are some dissipation, but the nature is not like, it cannot be modeled like viscosity. And finally, as I explained, there is a strong similarity with inertial wave turbulence. And I think it is interesting because we can imagine to better understand the solar wind turbulence with just a simple, a laboratory experiment. I can tell you that, but I usually do not say that to my colleagues because, of course, they want to develop instruments on spacecraft. So on this, what I will conclude, and I can take your question.
So thank you very much, Sébastien, for the very interesting talk. As you said, we can open the floor for questions. There is already a question in the chat, so maybe we can try to address that first. So the question is, does the theory assumes no background motion, hence no Doppler shift of the waves?
No background motion. In fact, yeah, for the velocity, yes, we for the model, I mean, we do not, for the turbulence model, we do not include a mean velocity if it is the equation. Yes, and for the observation comparison, we use the Taylor approximation. I don't know if it is if it corresponds to the question, but we can use a Taylor approximation because when we observe the solar wind with the spacecraft, the wind is so fast that during the observation, especially at electron MHD scale, you need like 1 minute of observation, and the plasma does not have time to evolve. The speed of the wind is like between 400 and 800 kilometers per second.
Okay, thank you for the
reply. And the speed of the wave was at the order of?
The speed of the wave is much. The speed of the wave is less, of course. It depends, but it is a good question. With the speed of the wave, it's like sorry, is it?
Because one could think that there is a Doppler shift of the speed of the wave.
No. The wave. Sorry, the speed of the wave is like if I translate in units, it's well, it depends where you are actually, but
yes, but it is much bigger than the speed of the solar wind.
Sorry, say again.
It is much bigger the speed of the wave. Is much bigger of the solar wind, or it is smaller?
No, the speed of the wind is fast. It's very fast. And actually, the problem with the wave is also that you see that it depends on, you don't have a single value. I mean, it's omega is k, z, k. So it depends on the angle. But the wind is, I mean, it's very fast. So you just really assume a Taylor. I mean, there are some, so I can answer differently. With the data, we have the possibility to take several spacecraft. I mean, the cluster differences. So people have tried, and they are motivated actually the mission, the space mission, to say we are going to improve the Taylor approximation by taking 4 points and to try to check if the Taylor assumption is valid or not for high frequency. And the result in terms of wave number spectrum is that the difference is really very small. And that means actually usually we don't use this technique to get information about the wave number spectrum. So we just take frequency spectrum.
So there is no need to modify the dispersion relation of the wave by including a Doppler shift. This is what you say.
This is the usual assumption, yes.
Thanks.
Thank you. So I see, Jim, please go ahead.
Yeah, I think that was really nice. Thank you very much. Excellent discussion. I don't really know a lot about electromagnetic turbulence, but I know about turbulence. So I wanted to ask if you could go back to the beginning, slide 6-ish, I think, where you show the spectrum and it transitions to, at the end of the spectrum, epsilon, meaning the dissipation rate. So I want to ask about the dissipation rate. I'm a little bit confused because this is a spectrum for the magnetic field, right?
Yeah. Yeah.
So is that the if you go forward to where you show your equations, I think there's a couple of slides in front of this. Next slides, you show the actual equations. Yeah, so are we talking about the dissipation in the magnetic field equation or the dissipation in the mechanical energy equation, which then goes into the thermal energy equation? Which dissipation are you referring to there?
Yeah, here in this equation, this is a really simple model. I mean, if I come back to the data here, what we understand, so let me just go back with my ladder. Okay, so here, this is indeed only B, so we should plot V. What we observe for V, it's limited. That's a problem. We can do simulation, of course. It's limited because for V, we need, we start with a distribution function, particles. So we need to resolve this distribution function to go back to V. And basically, we need one Hertz. So at this point where we start to dissipate, we lose information for the velocity. Of course, we can do simulations. Simulation shows that indeed the velocity, there are some dissipation, some damping. And but when you arrive to the -8/3, there is the velocity fluctuation is negligible. I mean, the kinetic energy is negligible. So when I say here dissipation, I mean for both U and B in principle. But when you arrive to high frequency, it's mainly B, mainly the magnetic field, I mean, in this modeling. And by dissipation, what do I mean? If I come back now here, of course, we need dissipation from the plasma physics point of view. It is not just a viscosity or a resistivity. So one way is to invoke, as I have shown after that, so maybe I can go here in this plot with this model. We have the possibility at this frequency to excite waves. And then when we arrive to this domain in plasma physics, dissipation means that we have interaction between waves and particles, damping of waves because of exchange of energy between waves and particles. And this is, I mean, basically dissipation. The way to dissipate energy in a medium where it is diluted, it's a big question. I mean, people use also what we call exact laws, the 4/5 law, but for MHD, compressible MHD, no whole MHD, to evaluate this epsilon and to just say, if we can do that at MHD scale, then we can just assume that epsilon must dissipate at small scales, by which mechanism is not clear, but we at least have an evaluation of the amount of energy if we assume that this epsilon is completely transformed into heating. But this is a big question in plasma physics.
Part of the reason why I'm asking my question is I went to another talk recently that talked about the propagation of alpha waves and their reflections, and this causing turbulence in the corona, and this maintains high temperature in the corona, but which means it has to go into thermal energy. The dissipation has to go, and being a classical hydrodynamicist, I think in terms of mechanical energy going into thermal energy, I don't really know how to interpret the dissipation in the magnetic field equation. So I'm asking, how does it go from the magnetic field turbulence, as it were, into dissipation that ends up in thermal energy? What's the path?
The path, I mean, usually when you say waves in the corona and so on, the people use just a classical MHD, nu on eta, and they do not care about the physics, the real physics here. So they just say, let's assume that it is very well modeled by that, but it is not correctly in plasma physics. Where I mean, again, I mean, if you know the Landau damping means that the wave gives energy to particles, and if you give energy to particles, that means you give kinetic energy. So if you have an electromagnetic waves, you can transform, like for Landau damping, means that the electrostatic field is damped and it gives energy to to electrons. So electrons get kinetic energy. So this is a way to.
And if you go back to the equations, what is that path in the equations that you just described in words?
It's not here. It's not here.
It's not there. Oh, that's why I can't see it then.
And because I am mainly interested by turbulence and mechanism. However, if you go, I mean, if you are curious and you go to this paper 2021 and 2022, the first is there are two kinds of simulations, and especially the second one, it's a peak simulation, so that means very precise simulation made with kinetic equation in plasma physics, and they explain that their model called I cannot read it, but it's called helicity barrier. Here is very well compatible with, in one way, the kinetic equation here, I mean the peak simulation, and also the fluid simulation where you have a correction to the equation that I have shown.
I see. Okay.
But you have to, because they want to model properly.
Right. Yeah.
Yeah.
All right. Thank you. Thank you very much. Appreciate it. Good talk.
So thank you. I see that there is another question inside the chat. So in rotating turbulence, in the wave turbulence regime, a large structure exists that's called geostrophic mode, mainly fed by wave interactions. Is there a similar mode in EMHD? And if yes, this mode, does it affect the waves?
Yeah, it is possible to have such structure because you also have the slow mode k parallel equals 0. So in principle, yes, but in this kind of simulation that I have shown, we have tried. Usually, we try to avoid to excite k parallel equal to 0. So, but in principle, yes, we can have this kind of structure, and we may have an interaction between the structure and the wave. So it's very close. So the answer is yes, but because we know that problem, we especially if we want to study the wave part, we try to be in a good situation. If I can compare with this experiment by Bonsalve, physical regulators like 2020 that I have shown for rotating turbulence, to observe inertial wave turbulence, they have put, you know that at the top and the bottom of the cylinder, some kind of how do you call that, kind of specific, I mean, boundary condition to kill this geostrophic mode and to get to better see the wave turbulence fluctuations. So this is also possible experimentally, but yeah, problems are similar. So yes, in principle, you can have this 2D structure.
Okay, thank you. Let's see if there are other questions from the chat or from the audience. So just feel free to unmute your mic or to write in the chat in case you have any question.
Can I quickly ask a question?
Go ahead, Christos.
Hello, Sébastien.
Hi.
You talked about monofractal statistics,
Yes.
or polyfractal, and you talked about the exponents, zeta p or psi p. Or so clearly you were looking at it, yeah, like here, for example. You considered fluxes through wave numbers, you said, but when you have such fluctuations, you will also have fluxes through space. They average to 0, of course, in your situation, but they fluctuate a lot. How can you account for any intermittency effect, fractal or monofractal or multifractal, without taking into account fluctuations of spatial fluxes, whether it is of energy or of magnetic field or whatever?
Space, you mean in the simulation? Simulations are in a box, periodic box. So
I know simulation periodic box and they are in wave number space. Of course, if you take one realization or one instant in time, you will see something which fluctuates, and there you will see gradients in space, which are non-zero. Of course, they average to 0, but they fluctuate around 0 violently, probably.
We take here, I mean, is it, I don't know if it is your, you see, for example, in the data, they take the modulus.
Yes.
Of P. So you take only the positive.
What is P? The moment.
So
this
this
the
is
exponent, yes. That is fine. That is fine. But just explaining what happens to p equals 4 or p equals 5 or even 3, without taking into account, which actually is something to do with fluctuations and intermittency here, without taking into account the fluctuations and the intermittency in the special fluxes themselves. Is that possible?
I'm not sure.
Do you understand what I'm saying? Perhaps I'm not saying it very well.
If I take, okay, let's say even that, I mean, here it's a simulation. You take, well, indeed, I mean, this is just in this kind of simulation that I show here. Usually we only use this kind of I would say, the goal is not to, I would say, model precisely what happened. We have to compare the data and simulation. So we use the same tools. So now if you say there are some, I think your question is deeper than this. It's just to understand better the intermittency. But in terms of data, if you compare the same quantities and you see a behavior that is only compatible with one regime, this is what we wanted to show, basically. Now, for studying turbulence in more precise way, we have to be more careful. I think this is your message. Is what you want to say?
Yeah, but I mean, actually, it's a shame you are not here. You are giving your presentation from Paris. Perhaps you would have had it would be easy to explain this. Anyway, I think thank you for your answer. Perhaps we can discuss this another time.
Yeah. Just the thing is that to complete my answer here, the fact that you observed in this simulation intermittency, there was like during 15 years a discussion, a debate about regime of turbulence at sub-MHD scale. And there is a group of people, well, they claim from the beginning that it's what we call critical balance. That means like you have two times and they balance each other. And because in MHD you observe that, we should also have the same regime at sub-MHD scale. So there was this claim, a lot of people believe that. But it was in contradiction with the observation about the monofractal that we have seen before and or after. And so that the big message for the SolarWind community is today, forget this slide, this model. It's not a good model for different reasons. And that I explained, the lack of intermittency and the fact that also it's 8/3. It was a big mystery. Why 8/3? And now we have a beginning of the answer, I think, with this collisionless prediction. But it's less. I mean, I would say this is a level of what we do, and I think we are. We'll say the next step would be to understand better and to model maybe better what happens. But
thank you, Sébastien. Thanks.
Okay, thank you.
So thank you. So we can see if there are other questions from the audience. Once again, just feel free to unmute your mic if you have a question, or you can write in the chat and I can report the question. That doesn't seem to be the case. So I have a question myself. So regarding the transient behavior you showed before, where you actually retrieved, yes, the 8/3. So what is the characteristic timescale of this transient behavior, and is it compatible with the observations? Because then you show the shift of the exponent for transition to the -5 halves, right?
Yeah, but in fact, the time scale here for the formation of that is basically the cascade time that you need to develop weak turbulence. Mm-hmm. But the point is that in a medium where there is no collision, then your spectrum can continue to smaller scales, yes. And with another power law and without a feedback like it is observed in this simulation. So in fact, the time scale in itself, so it's the time scale of wave turbulence, but it's not, the question is not, do we, because of the time scale, can we observe the feedback? I mean, the feedback, it belongs to another physics that is not applicable in the solar wind. So then just to go to smaller scales, and as you have seen, not in the spectrum that you have at the bottom, but we can measure, we can start to measure the scale even at smaller scale than this -8/3. And we see that the spectrum is steeper, so we can get actually prediction for that, yeah, so.
Okay. Yeah. That's yeah. It's clear that the physics is different because you were comparing collisionless with like viscous spectra, but that clearly that's different. I was just interested in how long will it take, like for the spectrum to develop. Yeah. Okay, cool. Thank you, and let's go for a last call if there are other questions. So, is there someone else who would like to ask a question? Just once again, feel free to unmute your mic if you have a question, or you can just write in the chat. Well, that doesn't seem to be the case. So thank you very much, Sébastien, for the very interesting talk and for replying to so many questions. And I invite our audience to thank our speaker again. So thank
you. La couper le son.
Thanks.
Thank you.
So see you hopefully next week. Bye.
Next week?
Yeah, we have a webinar per week, so we
yeah.
we tend to keep ongoing. So thanks again for today. Bye.
Bye.